Here is a pair of regular 6-sided dice. And this, on the other hand, is a slightly unusual pair of 6-sided dice. Believe it or not, if you roll each of these pairs and add up their respective totals, you get the same probability distribution of possible outcomes. My question is, can we find an alternate pair like this one for 8-sided dice? In other words, can we label two 8-sided dice with positive integers on each face, such that when you roll the pair and add the numbers on each of their faces, you get the same probability distribution for the possible outcomes as with regular 8-sided dice? I posed this question to my viewers in a previous video, and this is a compilation of the various approaches you all sent in. Before we dive in, we're going to be using these bar charts a lot, so I'll take a moment to explain what it means. Along the bottom of the chart, we have all the possible outcomes of rolling a regular pair of 8-sided dice, 2 through 16. The heights of the yellow bars indicate how many ways there are to roll a particular outcome. Sometimes, when we're considering an alternate pair of dice, you'll see me overlay some pink bars on top of the yellow ones. The heights of the pink bars represent the number of ways to roll each of these outcomes with the alternate pair. Most viewer responses, at least in part, contain some sort of computer program to search for a solution. There were many different versions of this. The simplest is a so-called brute force method. The idea here is straightforward. Construct every possible pair of dice, and for each one, check if that pair produces the target distribution. Let's do an example for the 4-sided case. Here's the probability distribution of totals for regular 4-sided dice. To find an alternate pair, let's start by setting each face on both of the dice to have a value of 1. Clearly, this doesn't produce the target distribution, so let's change the final face on the blue die to a 2, and now a 3, a 4, and so on. The maximum number for any given face in this example should definitely not be more than 7, because the maximum outcome in the target distribution is 8, and all of the faces need to have positive integers. So let's set this face back to 1, and change the next one over to a 2. We can keep on going here until we eventually either find a solution or exhaust all of the possibilities. Using this approach, we're filling in the values for 8 faces, and for each of those faces, we're checking each number from 1 to 7, so the total number of possibilities to churn through is 7 to the 8th power. In general, for n-sided dice, this number is 2n-1 to the 2n, because we're filling in the values for 2n faces, and for each of those faces, we're checking each number from 1 to 2n-1. Unfortunately, this is a huge search space to check, and while this algorithm is admittedly good enough to get through it for up to 4 and maybe 5-sided dice in a reasonable amount of time, anything past that is going to require some serious optimizations. With enough optimizations, many of you were able to make brute force search run fast enough to finish checking the 8-sided case. Here are a few that you all came up with. There are also several other similar optimizations that can be made, and a lot of these you would find by trying to do the problem by hand, which is exactly what some of you did. I also saw one submission that packaged up the constraints for these optimizations and some other ones into an integer program, which you can read about on Wikipedia if you'd like. There's another pretty neat programmatic method a few of you chose, which is the use of SMT solvers. These are tools that take a complicated mathematical statement involving lots of variables and try to find an assignment of numbers to those variables to satisfy the statement. The solver either gives you the solution it found or identifies that there is no such assignment. Here I've made a toy example with a couple constraints on some variables x and y, and the solver outputs x equals -3 and y equals 10. To solve the dice problem, we want the output of the solver to give us the values on each face of each die. These are our variables. And the constraints to satisfy should require that the chosen values for these faces create the correct target probability distribution. In theory, we have no proof that this approach should perform any better than the kind of brute force method we were just talking about. However, if you hang out around people who use these kinds of tools a lot, which I've had the pleasure of doing, the first thing you learn is that in practice they outperform all expectations due to the huge volume of engineering that goes into improving them. And indeed, a few of you were able to obtain the solution to this problem using an SMT solver in a matter of just minutes of computation time. It's pretty crazy that this empirical result lives in the same world where we have yet to prove very much about the theoretical hardness of satisfiability problems. By the way, this is the topic of a huge open problem in computer science, so if you do end up proving something about that, you would be famous. If you were looking closely, you might have noticed a similarity between the solutions for 4 and 6-sided dice, which is that the green die in these pairs is 1, 2, 2, 3 for 4-sided dice, and 1, 2, 2, 3, 3, 4 for a 6-sided dice. Many of you guessed that for the 8-sided case, maybe one of the dice in the pair would continue this pattern. It turns out that if we fix one of the dice like this, it becomes relatively easy to finish the search from there. In fact, I saw one solution that does it almost instantaneously with an inverse fast Fourier transform. But to show you just how easy this problem becomes when you fix one of the dice, we can actually do it by hand. We're locking in all the values on the green die, so now we'll try to find a blue die such that if we fill in the row plus column total in each cell, the correct number of each outcome appears in the final table. We need exactly one way to roll a 2, which means we have to make one of these faces a 1 to add with the 1 on the first die. Of course, there are some residual consequences of that, which produce all necessary ways to roll a 3, and leaves us needing just one more way to roll a 4. If we make the next face a 2, we would accidentally create too many ways to roll a 3 and a 4. Instead, let's make it a 3, and you'll see now that we have no issues. For the next blue face, putting a 3 or a 4 would mess up the earlier parts of the distribution again, so we'll end up settling on 5. We continue this process until the entire table is filled in. So there you go. You're looking at a solution to the problem for 8-sided dice. This method leads to one particular type of solution, that is, one where the green die follows the pattern extended from the 4 and 6-sided cases. And some viewers were able to show that this pattern continues in general for dice with an even number of sides. However, there are actually some other solutions too, which are best explained by the next method. This technique uses a clever algebraic abstraction to model our dice, and I'd like to take this opportunity to showcase an animation sent to me from Polyamath, which is another YouTube channel I think you'll really enjoy. He makes just breathtakingly beautiful videos, and I'd highly recommend checking them out. In this approach, a regular 8-sided die is represented with the polynomial x plus x squared plus x cubed all the way up to x to the 8th. What does this polynomial have anything to do with dice, you might ask? Good question. The key insight comes from noticing that if we take two of these polynomials, representing a pair of dice, and multiply them together, the result will be a new polynomial where for each term, the exponent represents one of the possible totals from rolling the two dice, and the coefficient counts how many ways there are to roll that total. Why does this happen? Well, think about all the ways you could multiply terms in the original two polynomials to get an exponent of, let's say, 3. There are two ways: x in the first polynomial times x squared in the second one, or x in the second polynomial times x squared in the first one. So when we accumulate all the terms at the end, the coefficient on x cubed will be 2. This is directly analogous to the reasoning that there are two ways to roll a 3, 1 and 2, and 2 and 1. If we change the exponents in our polynomials, it's equivalent to changing the numbers on the faces of the dice. This means we can reformulate the task of our problem as finding a new pair of polynomials with 8 terms each that, when multiplied together, gives the same product polynomial as we had before. To do this, it turns out to be very useful if we factor the polynomial for a normal 8-sided die. We get 4 factors: x, x plus 1, x squared plus 1, and x to the 4th plus 1. For now, don't worry too much about how we found these, but if you want to, you can multiply them together and verify that it gives the original polynomial. We can represent the multiplication of this polynomial by itself to get the target distribution polynomial by squaring each of these factors. Now we're ready to construct a new set of dice. The way we do that is by divvying up the factors into 2 groups whose expanded forms have 8 terms each. Here we've done that by taking the factors x, 2 copies of x plus 1, and x squared plus 1 for the first die, and x, x squared plus 1, and 2 copies of x to the 4th plus 1 for the second. Now all we need to do is multiply them back out, read off the exponents, and our new set of dice is complete. The solution on screen is the same as the one that we found earlier, but there are actually 2 more, and they come from the other 2 ways to rearrange these factors, producing 3 total alternative sets of dice. If you want to learn how to obtain those 4 factors without the use of a computational engine like Wolfram Alpha, there's a beautiful piece of math involving complex numbers. It's always lovely to see their unreasonable usefulness in discrete math problems. By the way, here's a picture that plots the number of alternate solutions for different numbers of sides, n. I was quite surprised at first to see just how chaotic this looks. In fact, let's zoom in on this first portion, and we'll highlight each of the points where the graph touches 0. Notice anything strange about these numbers? Yeah, it turns out that the values of n for which there are no alternate dice pairs are exactly the prime numbers. A lot of you noticed this, and I won't get into why it is the case, but the fact that rearranging factors plays a part in creating these alternate solutions should provide a foothold for that discovery if you want to take the plunge. I'm really just scratching the surface here. There's some crazy neat and complicated analysis that some of you were able to pull off, and for those of you who are interested, I'll post this PDF in my Discord server. Feel free to join and check it out. Up until now, I've presented to you the most common ways that viewers chose to solve this problem. However, there was one outlier that I really only saw from one particular individual. And this is not a contest, but if it was, I think I'd have to give the award for the most unexpected method to this one. Now, rest assured, you didn't mistakenly click away to a video about Tetris. These shapes really have something to do with rolling dice, which was as surprising to me when I saw it as it probably is to you. So where does this come from? If we go back to the method using colored tables, and we pause after setting the first blue face to a 1, let's take note of the shape of the distribution chart at that point. Suppose we made the next face a 9. This causes the same shape to appear a little farther to the right in the chart. And that makes sense because the green die is still the same. So the totals created with the blue face of 9 are all just 8 more than the totals created with the blue face of 1. If we decrease the value on that new blue face, the shape moves to the left, 1 by 1, until eventually overlapping with the original part of the chart, which happens because there's now some overlap in the possible outcomes of adding the green die with these 2 blue faces. The idea this viewer had is to interpret that overlapping as dropping the new shape on top of the old one, sort of like Tetris. And if we can drop 8 copies together in a way that fills up the overall shape for the target distribution, we've found the 8 faces for the blue die. Here comes another clever trick. Let's change that target shape a little bit to look more like a staircase than a pyramid. which really still represents the same distribution because the heights of the bars are unchanged. And we'll also change the shape by lifting up this one square at the end, which for the same reason represents the same green die as before. This viewer found that if you do this, you can actually tile these shapes right next to each other instead of having to drop them. We already knew that this green die would yield a solution, since we saw it earlier in the video. However, this viewer was also able to find 3 other shapes that work, altogether corresponding to the 4 solutions to the problem, including the trivial one for regular dice. This viewer managed to turn a problem about probabilities of rolling dice into a problem about tiling shapes together, which I thought was just beautiful. I love sharing these kinds of puzzles with you all because it puts on such a great display of how one simply stated question can invite so many different problem-solving techniques and perspectives to the table, each of which opens new doors waiting to be explored. Getting exposure to all of these different approaches definitely helps bolster my problem-solving ability. If you want more practice with concepts in math and science to help sharpen your own skills, I highly recommend you check out the sponsor of this video, Brilliant. Brilliant has tons of interactive lessons in a wide variety of technical fields, including math, computer science, physics, chemistry, you name it. Brilliant is designed to be uniquely effective. Their first principles approach helps you build understanding from the ground up. Recently, I've been using Brilliant to learn about math history, and there's so much thought and attention to detail put into each one of their courses. They provide such a high-quality, refreshing, and fun learning experience. These lessons are packaged into easy-to-use graphical interfaces, so you can learn on the go from anywhere with a mobile device, helping you maintain a habit of learning every day with just a few minutes of commitment. In their latest course on how LLMs work, you'll get to peek under the hood of large language models like ChatGPT to understand the concepts powering today's technology. To try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org/purplemind or scan the QR code on screen. Or you can click on the link in the description. You'll also get 20% off an annual premium subscription. Huge thanks to Brilliant for sponsoring this video, and to everyone who submitted something for this problem. And by the way, if you are one of these people but you didn't see your name mentioned earlier in the video, your involvement with this whole project is just as important to me as anyone else's, and it didn't fly under the radar. As you can see, there were several dozens of people who sent in their work, which is awesome. The caveat is that it's unfortunately impossible to cover all of it in full detail. That being said, I had so much fun trying to make sense of and put together all of these different methods, and certainly learned a lot in the process. I hope you did too. And as always, thanks for watching.